EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. In the last few videos, we learned how to set the unit system and obtain some basic properties for real fluids. These were property functions that all applied to single-phase pure substances or a mixture with a specified concentration. These tables show the basic thermodynamic and transport properties that we've looked at so far, and they all require two properties in order to fix the state according to the phase rule. There are another series of functions that require only a single property to fix the state because they refer specifically to a two-phase situation, and according to the phase rule, a single property will fix the state in a two-phase region. These are listed here and include things like the enthalpy of vaporization, saturation, pressure and temperature, and surface tension. The saturation temperature corresponds to the temperature at which a pure fluid evaporates, and therefore it requires only a pressure. So here the saturation temperature of R134a at a pressure of 100 kilopascal is determined to be 246.8 Kelvin. The saturation pressure is the pressure at which a pure fluid evaporates, and therefore it requires only the temperature. So here the saturation pressure of R134a at 246.8 Kelvin is determined to be 100 kilopascal. Note that mixtures do not in general evaporate at constant temperature for a given pressure, and therefore the functions Tsat and Psat cannot be used for a fixed composition mixture. So for example, R507A, Tsat won't work for that. The function enthalpy vaporization provides the change in the specific enthalpy between saturated liquid and saturated vapor at a given temperature or pressure. It will provide the answer on either a mass or a molar basis depending on how the units are set up. So here I'm getting the enthalpy of vaporization of R134a at a temperature of 300 Kelvin. And I'll get the same answer if I call enthalpy vaporization using pressure if I use the saturation pressure at 300 Kelvin. And you can see that here. The enthalpy of vaporization is defined for mixtures, as it's of course possible to compute the enthalpy of saturated liquid and the enthalpy of saturated vapor at a given temperature or pressure. And so here I'm getting the enthalpy of vaporization of R507A at a certain temperature, and here I'm getting it at a certain pressure. Finally, surface tension is defined for a liquid-vapor interface, and therefore is only valid for a two-phase state where saturated liquid and saturated vapor are coexisting. The surface tension function requires the name of the fluid and a temperature. So here I'm getting it for R134a. And surface tension is also defined for a mixture. So here I'm getting the surface tension of R507a. There are another series of functions that only require the name of the fluid and nothing else, and those are shown here. And these include functions that provide characteristics of the molecular structure and interactions associated with the fluid molecules. So these are things like molar mass, dipole moment, and Lennard-Jones energy and length potential. So the molar mass of any fluid in the database can be obtained with the molar mass function. If you call it with a mixture here, you'll get the effective molar mass of the mixture. There are some functions like the Lennard-Jones energy potential that aren't applicable for mixture, so you can't use that one for a mixture. Other functions in this table provide characteristics of the vapor dome, so critical temperature, pressure, and specific volume, triple point temperature, and the normal boiling point and enthalpy of fusion are all characteristics of the vapor dome. The function fluid type $ is a string function, and it only requires the name of the fluid, and it will give back the type of fluid model that's being used for that fluid. So these correspond exactly to the categories that are identified in this palette here in the thermophysical properties window. So real, ideal, brine, or incompressible. And these other two are also classified as ideal gas. Using this function with any of the real fluids here will return the string real. If I use it with any of these ideal gas fluids, I'll get ideal, and so on. So this is one of a series of tutorials meant to describe the operation of the EASE software. If you want to get more information about EASE, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering EASE, which can also be obtained from the FChart website.